Hi, the lecture today is about the derivative of logarithmic functions. So let's get started on that. Let me quickly review some of the items that we need here and will be referred to. You remember the exponential of x. That's just like 2 to the power of x or something like that, and that e was the number 2.718 and so on. So it's just a number, graph of exponential of x quickly, something looking like this. And among all those functions that we studied with a similar graph, this one stood out by the fact that it had the slope of 1 at x equal to 0. The formula for the derivative of this was the easiest formula. E to the x, the derivative is just itself. If you want to apply the chain rule, if instead of x you have some function of x, the derivative is just a copy of itself times the derivative of the exponent, whatever that might be. Really, if you wish, you can put x prime here as well if you want to make the formulas this look the same, but x prime is just 1, so the formula does not get to have that. One other item is what if you had some other number other than x, other than e, you want to differentiate. Well, the derivative turns out to be a copy of itself times the natural logarithm of the base. And if you have 2 to the power of u and you want to differentiate that, it will be a copy of the function. Then by the chain rule you are going to have the derivative of exponent, and then you still have logarithm of the base. In general, if you have any number raised to power of x, the derivative of that is going to be the function itself times logarithm of the base you're using. And if b is raised to some other entity, you just do as above, you copy it, differentiate the exponent, and multiply with the logarithm of the base. Now what we want to do is to look at a derivative of logarithm. That is, what if I had logarithm of x in some base and I want to differentiate that? That's our question. I go ahead and give the formula in, do some examples, and then later on I'll come back and explain where the formula itself comes from. The derivative of logarithm of x in some base is 1 over x. In the denominator we are going to have logarithm of that base. So for example, if I have logarithm of x in base 5 and I want to differentiate this, of course with respect to x, our answer would be 1 over x logarithm of 5. And let's go ahead and mention the chain rule while we are talking about this. If you have logarithm of something other than x, a function of x, so all over here u is just representing some function of x, and we are differentiating everything with respect to x. By the chain rule I have to multiply with the derivative of the substitution as well. So I'll have u prime over u and then logarithm of b. So in this case, if I had logarithm of u in base 5 and I want to differentiate, I will have u prime over u logarithm of 5. Whatever u might be, it's going to be used there. among all the logarithms, natural logarithm stands out, so let's go practice that. So you remember, ln, when we write ln, it stands for logarithm in base e. So for that reason, logarithm of e itself, which is logarithm of e in base e, natural log of e, which is same as this, is going to be 1. So keep that in mind. You might want to go ahead, do a quick review of properties of logarithm. And here are formula for the logarithm. If I have natural log of u and, natural log of, let's say, x, and I want to differentiate that, the formula is just like this, except that I have to write natural log of e here, and natural log of e is 1. So the formula becomes extremely simple, becomes 1 over x. Let's repeat the same thing for the chain rule application. Logarithm of u differentiated is going to be the derivative of the substitution divided by the substitution itself. So it's just like this formula, and just gets multiplied by u prime. Let's go ahead and have some examples. Suppose we take the following. Find derivative of logarithm of x squared plus 1. Well, here's a rule that needs to be applied to this one. X squared plus 1, that's a substitution, has to be differentiated, and we are dividing it by the original expression. Numerator we differentiate as we have learned, and by now we are done. That was it. Let's try another one. Suppose I had logarithm of, say, radical x plus 1. I want to differentiate this. I have to differentiate the substitution and divide by the substitution. Derivative of radical x plus 1 is 1 over 2 radical x. As hopefully you know by now, you write this in power notation and differentiate, but you better memorize that because you're going to see it very often. Now I can bring this in the denominator and multiply through. Maybe you can go ahead and do that for me. Take 2 radical x, multiply by this. Radical times radical, x is going to be released, and then another 2 radical x comes in the denominator. Let's mix some of these with the previous examples we had. Say logarithm of sine of x. Say I want to differentiate this. I have to differentiate the substitution and divide by the substitution. So it's going to be cosine of x over sine of x, and hopefully remember cosine over sine is cotangent of x. At the beginning of calculus 2 or end of this course, you will need to remember that this thing showed up here. So we might as well go ahead and make some case out of this for future use. It wasn't just an example, but something nice happened. What is so nice about this? If the output of a differentiation problem turns out to be some basic simple function, then we essentially have discovered something. We have discovered what function is it that if you differentiate that, you come back to this some function we know. That's going to be second preoccupation of us for us in this semester later on. So I just wrote this thing down here. And let's go ahead and try something else. Suppose I have natural log of, let's try something else, cosine of x. You can guess what's going to happen. I have to differentiate cosine, divide by cosine. Derivative of cosine is minus sine now we get minus tangent. Let me write it in this fashion. If I want to move this tangent minus out of sight, then I have to move it to the other side. So I might want to write it like this: minus logarithm of cosine of x. If you differentiate that, you're going to get tangent of x. So why did we move the minus to the other side? It's just a question of aesthetics, really, no substantial thing in mathematics. And tangent of x is a basic function we are familiar with. We might be curious about what is it that I can differentiate that's going to produce this function I know. Okay, again, that's a preoccupation for us next second half of the semester. Okay, let's go ahead and recap what we have so far. We have the following formula. We have logarithm of something. If you differentiate that, you get u prime over u. So we practice this formula. Next formula we want to practice is what if my logarithm was in a base other than the base e? You remember if a base is something other than e, then the logarithm of that base comes in the denominator. So let's go ahead and emphasize that in the context of some of these examples. So remember this in mind. If you have logarithm of something in a base other than e, this is the formula that's applicable. Derivative of the substitution divided by substitution times the logarithm of the base you're using. Let's go ahead and take a look at, for example, what is logarithm of, suppose I take logarithm base 7 of x squared minus x, and I want to differentiate this. Here are three components of it: derivative of your substitution, the substitution itself in the denominator, and then logarithm, natural log of the base you're using here. Essentially you're doing a change of bases. So this turns out to be 2x minus 1 over x squared minus x times logarithm of 7. That's it. So let me write down this other formula next to this for emphasis. You have logarithm of u in some base b, and you want to differentiate that. You have u prime over u natural log of b, and then that's it. Okay, for the students who are curious, where does this formula come from? You know, we just can say some formula and just memorize it. There isn't enough substance in that. So let's go to the next level. Why is that so? Suppose I take a function y, call it logarithm of x in base b. Question is, what is the derivative of this? What's y prime? Well, if you remember from the beginning of the semester, or if you wish to go back to text on logarithm or chapter 1 of this text, this means that x is what is that? X is b to power of y. Remember that? For example, when you say 3 is a logarithm of 8 in base 2, you're rephrasing the following statement that 8 is equal to 2 cubed. This is same as that. In general, when you say logarithm of x in base b, what you mean is that if you take this base and raise it to that, you're going to take x back. So we start from here and work our way to get y prime. So I go ahead and say if x is equal to by, then x, the derivative of the left, has to be same as the derivative of the right. Derivative of x is 1. Derivative of b to the power of y. Take you back to this item, derivative of b to something. Derivative of b to something is a copy of that times derivative of the substitution times the logarithm of the base, and that is what we are using here. Copy of this, derivative of the substitution times logarithm of the base. So if I want to find y prime, I can say 1 divided by b to power of y times logarithm of b. Next layer, who was b to power of y? B to power of y was just same as x. I go ahead and substitute here. So y prime becomes 1 over x times logarithm of b. So once again, if y is logarithm of x in base b, then its derivative is 1 over x times logarithm of b. So that concludes the proof of the theorem that we are using, the rule that we are using. Now we go ahead and do some more applications. Next application we have in mind is something called logarithmic differentiation. Logarithmic differentiation is a style of differentiating functions that appear too complicated. Only certain class of functions are eligible for this, and that is functions that are made out of multiplication, division, and exponentiation. So if your function is mainly made out of multiplication, division, and exponentiation, then this rule will be helpful. Otherwise, it's not going to do much for you. Let's go ahead and take an example and show you in the context of example how does this go. Suppose I have a function, call it y equal to, let me just pick something from say 2x plus 5 to power of 10 times say cube root of say x squared plus x, something like that. This is still not all that bad, but we don't want to go overboard with these things. Question is, how do you find y prime? Of course, you have available to yourself the product rule and quotient rule and all of those things, and you could use those to answer the question here. But let's try something else, and the method we are going to develop is going to be applicable in cases where all those rules, product rule or quotient rule, wouldn't be applicable. What do we do here? First, we notice that this function has a lot of powers in it, built into it, powers or radicals, that's the same thing, and multiplication. Of course, there are some minor additions here and there also, but the main flavor of the function is you have lots of powers and then eventually a multiplication. What does logarithm do for us? Logarithm, we intend to use rules of logarithm to clean this thing up. First of all, we write everything in a power notation. If it isn't, we just force it to be like that. So I write x squared plus x to power of 1/3 here. Now I take natural log. Natural log of the right hand side. Let's write step by step. If I have natural log of this, I remind myself from properties of logarithm, if you have logarithm of a product, is the logarithm of the first plus logarithm of the second. Okay, logarithm converts multiplication to this type of addition. That's a claim to fame of the logarithm. So I go ahead and then say this is logarithm of 2x plus 5 to power of 10 and logarithm of x squared plus x to power of 1/3. Then they are added to each other. Second rule of logarithms is if you have logarithm of a power of something, that power could be brought in front. That's the second reason logarithm is such a useful thing. So this came here. What does that do? The 10s come up front. This becomes 10 logarithm of 2x plus 5 plus 1/3 of logarithm of x squared plus x. So once you do several of these examples, hopefully you'll be able to go from here directly to here. Let me rewrite again. This is logarithm of y is equal to exponent up front. The logarithm of each base is taken. Multiplication turns into addition, and if you have division, it will turn into subtraction. Now what? Now the what of it is that you can differentiate this. I can differentiate, instead of rewriting this, let me use this facility here and indicate we are differentiating both sides. Well, how do you differentiate? You remember derivative of logarithm of something is just derivative of that substitution divided by itself. Same thing on the right hand side. I have to differentiate that, and then by rule of linearity I can multiply with these guys later. So I say 10 times derivative of logarithm of 2x plus 5 is 2x plus 5 differentiated divided by itself. Derivative of this one divided by itself. Now I go ahead and actually carry out the differentiation. Y prime over y, 2x plus 5 differentiated gives me 2. 2 times 10 is 20. Here it's 1/3 of 2x plus 1, or you could leave the 1/3 up front, either way. You remember the question was what is y prime? Our aim was to catch y prime. So I might as well move this y to the right hand side. How do I move it to the right hand side? Just multiply by y. Y times all of that stuff. So 20 over 2x plus 5 plus 1/3 of 2x plus 1 over x squared plus x. If you want, go back and see what y was to begin with. Y was all of this, or even this other form of it. That is the y. If you want to write the final answer in its full glory, you maybe we want to go back and convert y to its original. It was 2x plus 5 to power of I already forgot, it was to power of 10, I guess. And the other portion was cube root of x squared plus x. So all of this is this y. And then we continue with this thing up front, 20 over 2x plus 5. And this 1/3 is bothering me over there. So 2x plus 1, I might as well put it in the denominator, 3x squared plus x. So that's the derivative. You see that the derivative, we started with this expression, that's the y. The derivative is this multiple of the original function. That's the common flavor of this kind of differentiation problems. Now, to show you some other examples which are more interesting than the one we just did, let me ask you to follow the following conversation, which is So here is an interesting or more advanced example. Suppose we have this function say x. Find y prime. You're trying to find the derivative of this expression. This is the first time you're seeing this, unless you saw it in high school. What is so different about this? You have seen two kind of examples. For example, you have seen derivative of something raised to power of x, and you have seen derivative of x raised to power of something. Either the variable was in the exponent or the variable was in the base. In both of these cases, you have seen the other number that was involved was some constant. Perhaps it was 2 to the power of x, or x to the power of 10, or something. This is probably the first time you see a situation where both the base and exponent are functions of x. And the formula in this case becomes essentially the most complicated differentiation formula you have seen. How do we get to it? Easiest way to arrive at it is by logarithmic differentiation. This is an example that needs it. The other ones you could get by doing a lot of other kind of rules, but this one would not be doable without the logarithmic differentiation. In calculus 2 or calculus 3, you'll see some other ways of approaching this question, but right now this is the way. We are going to take a logarithm. I'm going to take a logarithm of this one as well. Logarithm of x2 plus 1 to the power of x cubed plus x. Okay, so the logarithm of this whole thing is being taken. You remember we said property of logarithm is that exponent comes up front. That's what is coming to our rescue. That the exponent comes up front here, becomes x cubed plus x times logarithm of x squared plus 1. Now I have to differentiate. Differentiating logarithm of y gives me y prime over y. On the right hand side, well, I have to do whatever I need to do here. I pay attention that here is a multiplication, so I have to apply the product rule. Product rule tells me differentiate the first item, so let me write the steps. X cubed plus x has to be differentiated, and then you multiply that with the second entry, plus x cubed plus x has to be multiplied with the derivative of the second piece. Now let's go ahead and do this. Y prime over y, derivative of the first is 3x squared plus 1 times logarithm of x squared plus 1, and the second piece is x cubed plus x. Derivative of that logarithm, we have seen examples like this. You put the substitution in the denominator, you take the derivative of this and put it in the numerator. So it looks like we are done with the differentiation. All that I need to do is to carry this to the right hand side. So what was y? Y, if you remember, was x squared plus 1 to x cubed plus x times this whole mess. So yeah, I have to rewrite all of that. Unfortunately, we could not expect the problem to be simple short, but okay, here's the answer in its full glory, or if you wish, in its full horror. This is the whole thing. We are done with the differentiation. Just for illustration purposes, I go ahead and do one simplification here, just to bring some point home. I'm going to multiply through. There isn't really much of simplification to do except one thing. This factor x squared plus 1 shows up in the denominator here as well. So this is being raised to some exponent and it's being divided here to exponent 1. Is that right? You're dividing this by exponent 1. So I can take that exponent and this exponent and subtract them from each other. So let's go ahead and do this. This becomes x squared plus 1 x cubed plus x times this second piece is going to become this raised to that exponent you're dividing by x squared plus 1, so I have to subtract. I subtracted this 1 from the exponent there. Now I have to multiply still with what I had here, which is x cubed plus x and then times 2x. Let's see if we can see anything in this mess, which is the following. Let me try to make some other notation. Suppose our base was u, this was our base, and this is our v. Let's see if that removed the clutter. What we are getting out of this when we are differentiating is here u, this is u, that is v, that is the derivative of v, so let's write u v. This guy is just derivative of that, it's a v prime, and this one is the logarithm of the base. Now let's move on to the next one. This is u, that is v, this is v minus 1, u to the power of v minus 1. This is v, and this is u prime. So this is really what is going on here. This was really a big mess. Was hard to see what's going on, but what is behind all of that is captured in this formula that I just wrote here. Now, this formula is not really all that bad. I want to emphasize to you that this portion you have seen before and this portion you have seen before. All that is new here, that the two of them get to be added to each other. Where have you seen this one? Well, let me remind you of a situation like this. If you had a question like x squared plus 1 to power of 5, how would you have differentiate that? You would have taken that and reduced the exponent. You would have made it as x squared plus 1 to power of 4, just like here you're subtracting 1. You would have brought that exponent up front, the 5 would have come here, and we would have multiplied by the derivative of the base, that 2x. So what is happening here is that when you have u to the power of v in this section of it, this is being treated as if v were a constant. If v were a constant, didn't have any x in it, you would have differentiated it like this. You would have reduced the exponent one notch, brought the exponent up front, and you would have multiplied with the derivative of the base. That is exactly what's going on here. Well, what's the meaning of this portion? If you had an expression like this, say 5 to the power of x cubed, let me write it further back so I have room. If you had 5 to the power of x cubed plus x, and you wanted to differentiate that, what would you do? You would have copied it through, by the chain rule. You would have multiplied by the derivative of the substitution there, which is 3x squared plus 1, and then by the rule we just mentioned at the beginning of the hour, we would have multiplied by the logarithm of the base. That's a logarithm of 5. Well, that is exactly what you are doing here. You are treating this component as if u were a constant and v were a variable. In that case, the derivative would have been a copy of the original times by the chain rule multiplied by the derivative of the exponent times a logarithm of the base. So really what you are doing here in this most complicated formula you have seen is combination of two formulas. Let's go ahead and refresh our memories on those two formulas we saw at the beginning of the hour. If I had b raised to power of something, say v, and I wanted to differentiate that, and v here is taken to mean some function of x, b is taken to mean some constant. This is how I would have differentiated that, b to power of v, v prime, and then logarithm of b. And if I had u to some power n and I wanted to differentiate that, I would have had u to the power of n minus 1 multiplied by this exponent n and multiplied by the derivative of the base. So we have this formula applicable when n is a constant, the exponent is a constant. This formula when the base is a constant. And when both of them are variable, both of these contributions come in and they get added to each other. And then you'll have more on this thing in Calculus 2 or Calculus 3. This idea of, let's for a moment treat u as a constant, let's for a moment treat v as a constant, let's get the two derivatives and then add them up to each other, is going to come into you as an advanced form of the chain rule. Okay, to finish the lecture today, let me go back to something about the number e. So our next topic is this mysterious number e. E, we said several times, is some number whose first few decimal places are just these that I wrote, 2.71828, and so on it goes. Where does e come from? First place we saw this, we said if you take a look at a various exponential function, like if you look at 2 to the power of x, it looks something like this. If you look at say 3 to the power of x, it looks something like perhaps like this. This one, 2 to the power of x, has some slope here, which we just have said is actually logarithm of 2. 3 to the power of x has some slope here. As you change this base, that slope changes. It just turns up. Well, e shows up in this context like this. It's the function that goes up. E to the x is the function that goes up, and its slope at the start is 1. So it stands out among all the others. Slope of the tangent line at this point, it is 1. Let's just remind ourselves, what does that mean? How would you take the derivative of e to the x? From material at the beginning of the class, this is limit of exponential of x plus h minus e to the x over h. We simplify this by saying e to the x can be factored out, and you are left with limit of e to the h minus 1 over h as h goes to 0. If you wish, take x equal to 0, excuse me. So slope of, forgot to put the prime here, slope of e to the x at the y-intercept at x equal to 0 is, put the x equal to 0 here, and you get limit of e to the h minus 1 over h as h goes to 0. That e is adjusted so that that slope turns out to be 1. Now let's go ahead and look at this formula a little bit. What we are really saying is e to the h minus 1 over h gets closer and closer to 1 as h comes closer and closer to 0. Let me go do a little bit of arithmetic here that's perhaps a bit unfamiliar to you, but I multiply both sides by h, so e to the h minus 1 comes close to h as h goes to 0. Now I'm going to move this 1 to the other side and write it as e to the h approaches 1 plus h as h goes to 0. Finally, I'm going to take the h and take a h root of this. So from both sides, e to the h, I'm going to raise both sides to the power of 1 over h. Why am I doing this? I'm just removing all the clutter from around e and moving it all to the other side. So by now, all h has moved to the other side, and I have 1 plus h to power of 1 over h, and here is just an e. As h goes to 0, this expression is your variable expression, and it's going to approach e. So let's draw the arrow the other way around. Now we have the following final conclusion, that limit of 1 plus h to the power of 1 over h as h goes to 0 is going to be that number e. So this is one way of talking about the number e. There are many, many ways of writing this number, this famous number, and this is one of them. If you want to get a feeling for what we just talked about, it's good for you to pick up your calculator and just try this. Like take h, like I take h to be, say, 0.01. What does that become? It becomes 1 plus 0.01 raised to the power of 1 over 0.01, which is really 1.01. Reciprocal of 0.01 is 100. Go ahead and find this thing out. See how many digits of e do you recover from here. Here's e, 2.71828, and so on. As you use h that is smaller and smaller, and exponent's going to grow larger and larger, the number that you are going to get is going to get closer and closer to this special number, 2.718, and so on. So I leave that to you, and you go ahead and do the exercises of this section. Essentially a lot more differentiation formulas and practices. Perhaps the only interesting thing in the whole conversation was this one, where that came from, and the other formula of interest in the whole thing perhaps was that. But you go ahead and take a couple of examples from each of these types and get ready for the next test. Okay, good luck and God bless.